Hi, everyone. My name is Ariel Boyarsky. I'm a PhD student at Columbia Business School in the DRO division, and I'm presenting joint work with my advisor, Hongseok Namkoong, and Pouget-Abadie from Google Research. Today, we're going to talk about experimentation in the presence of interference and a novel approach to addressing this challenge. Without spoiling anything, I'm first going to give the setting of the problem we're trying to solve, and I'll motivate this using an example from experimentation in auctions. Then, to highlight our contribution, I'm going to show you how we can use our proposed methodology to solve two different problems. First, how we can choose between different models of interference, and second, how we can use those models to then identify causal effects. So to motivate our discussion here, I want to start by thinking about what makes a good decision. I'm going to argue that to make a good decision, we need to base them on causal relationships. But ascertaining causal relationships is hard. The gold standard for this is to run a randomized experiment called an A/B test in tech. For example, in an auction setting, we want to determine which reserve price policy is more profitable. However, I can't both know the outcome under policy A and policy B. That is, if I gave an individual a price under policy A, I can't also give that individual the price under policy B and be able to know both outcomes at the same time. This is called the fundamental problem of causal inference, in that we need to identify counterfactual quantities. To be able to concretely write down these counterfactual states of the world, I'm going to use what's known as the potential outcomes framework. This framework defines what the outcome would have been had we used a particular treatment option for the individual. For each unit, we're going to randomly assign a treatment denoted by Z, which is either 0 or 1. You can think of this as either A or B. And we're going to have potential outcomes yi of 1 and yi of 0 denote different counterfactual states of the world. We're interested in the difference of these quantities, but we can never observe both at the same time. If we observe yi of zi, we can't also observe yi of 1 minus zi. In the OR and ML literature, this is also sometimes called banded feedback. So, using this framework, we're going to try to tackle the problem of interference. This happens when there are unaccounted for spillover effects between units. That is, an individual outcome does not only depend on their own treatment status, but on the treatment status of others. If you remember from our previous framework, a major assumption is that our outcomes depend only on our own treatments. So this is a major violation of the potential outcomes model, as it breaks the mapping from treatment status to outcomes. Interference is also extremely common. For instance, in marketplaces like ride-sharing platforms, this could happen if you incentivize more drivers to drive and they cannibalize the demand of new drivers, for instance. And so it's hard to know if your incentive is actually working or not. It also happens in vaccine trials, where there might be spillover effects if treated and control individuals interact. So to tackle this problem, we're going to use something called a rollout or ramp-up experimental design. These designs are a universal experimental framework, and the infrastructure to run these experiments is ubiquitous throughout industry and especially in technology companies. The idea is that we will successively treat more and more individuals and evaluate our policy at each period. So in each period, we choose some individuals to be treated and evaluate the policy. Then we choose some more individuals to be treated and again evaluate the policy. If the policy turns out to not be working well, we may revert. We're going to try to exploit this structure to learn a little bit about the interference patterns. In our paper, we're only going to consider rollouts at 50%, since we want to be able to determine whether or not a policy is good or not, and then and only then roll out to everybody. The important thing to note is that by increasing the number of individuals who are treated, I'm inducing temporal variation in treatment exposure and thus the interference effects. That is, there is no interference. That is, if there is no interference, then this design is not going to change our estimates of how well a policy performs. But if there are interference effects, then we should expect to see some fluctuations in our estimate of how well a policy is performing. Many people have studied interference before. Most of these approaches, however, take a model-based or design-based approach where they try to say interference is going to follow a particular structure, and given that structure, they will try to estimate treatment effects. Unfortunately, in practice, many of these structures are unpalatable, and models can vary widely. Our focus instead is on model selection. Given multiple different possible models for interference, how can we choose a model that best fits our data and best fits the interference structure, and then allows us to estimate treatment effects. So in our main contribution here is to propose a model selection method and estimation framework that's going to be based on these rollout designs that we introduced. So to kind of motivate this and make things more concrete, I want to give an example using second price search auctions. We want to test whether a particular policy for choosing the reserve price in these auctions is actually increasing overall revenue. In this case, our treatment Z will be an indicator of receiving the pricing policy, and Y will be our observed total revenue from an auction. As we will see, even though our Z can be randomly assigned, we can still have problems in trying to estimate our treatment effect if there's interference or spillover effects. So in this case, we're going to have two keywords. We're going to have the iPhone keyword and Google Pixel keyword that individuals search, and we're going to have one ad that displays for each keyword. We're going to have one bidder to simplify things. Of course, this is a very stylized example to showcase how interference can affect experimental designs. And in this case, we'll have this bidder be Verizon, and Verizon is going to bid on the auction that maximizes their utility. And we're going to assume that they have a budget constraint so that they can only ever bid on one auction. In this case, utility is given by the value minus the price, since it's a second price auction. And Verizon chooses to bid on the Google Pixel keyword, and we get revenue P2, since they pay the reserve price. Now suppose we run a naive A/B test. In this A/B test, we're just going to treat the Google Pixel keyword, and we're going to use iPhone as our control. Since Verizon's budget constraint binds, they have to bid on the keyword that is maximizing their utility. And since we've increased the reserve price for P2, we've eroded that utility. And so instead, Verizon bids on iPhone, which means we get revenue P1, which is actually a decrease in our revenue. This is actually quite weird because we've increased prices and yet we're seeing a decrease in revenue. So how can we explain this? Well, what's actually happening is that we're not really looking at the counterfactual of interest that we should be. We're not really interested in what happens when one keyword gets this policy. We're interested in what happens when everybody gets this policy, when both keywords get this policy. And in that case, we preserve the utility that Verizon gets in Google Pixel, and our revenue actually increases to P2 star, the new reserve price. So the issue, what's actually happening here, is that there's a spillover effect in our A/B test between our iPhone and Google Pixel auctions. So even though we've assigned our treatment randomly, this spillover means that our estimate is not indicative of what we should be getting had we treated both keywords at the same time. So how do we actually tackle this? The main approach to this is to create a model of interference that explains these spillover effects. However, determining such a model is hard and it's often impossible. So we need to be able to figure out whose treatment status actually matters for the outcome of I's outcome. But there's a lot of ways that we could possibly create such a mapping. So to illustrate this, in our previous example, we can consider this case where we could build an interference model based on how much a bidder bids, which is showcased on the left, versus interference graph of how much they bid and win, which is showcased on the right. In both cases, we see two different interference networks for how the keywords are interacting with each other, where the spillover effects actually are. And so we need to have a way of somehow distinguishing between these two models. As you can see, this is actually quite difficult because even though we might hold our actual mapping from the treatment statuses to the outcomes F the same, the way we determine which treatment statuses are even important to consider could be vastly different. So what we really need to do is to find a way to induce variation into our treatment effect that we can use to then learn a little bit about how interference is affecting our outcomes, which is why we turn to the rollout designs. Rollouts provide us additional variation in the outcome treatment exposure that actually makes model selection possible. For example, we can consider a rollout in our previous example. What this looks like is that we have some underlying interference network. For example, we could construct this using one of the two previous methods, winning bids or bid amounts. Thus, the advertiser will create edges between the keywords for that advertiser. And we'll start with no one being treated. Then we'll randomly select one of these keywords to get treated, and we'll look at the outcomes again. And then we'll select another keyword to be treated. And we'll see fluctuations in our revenue across each of these periods. The important thing to realize here is that as we treat more and more individuals, or in this case, keywords, we get to see how their outcomes change as a function of treatment exposure, which lends insight into the underlying network structure and the form of interference. So how do we actually operationalize this intuition? Our approach here is going to be to exploit the rollouts, and we're going to come up with a kind of leave one out cross-validation approach, but for periods. So what we're going to do is we're going to have big T periods given to us of our rollout, and we're going to fix one of these periods, and we're going to try to predict the outcomes for that fixed period using all the other periods as a kind of training set. Our intuition here is that by tempering our model against all the periods and then selecting the model that does the best job in predicting outcomes across all of these periods, we're picking a model that is tempered against different levels of treatment exposure. And so that we are picking a model that is best fitting our underlying interference structure. Of course, this is just a heuristic, and other procedures exist that might perform well. But in practice and in our testing, we find that this procedure does a pretty good job of selecting the true model in many different test cases, which I'm going to show to you now. So the first test that we run here is we're going to run simulations where we vary the underlying sparsity of the interference network. This is a pretty important test case because in many cases, we're going to find that interference networks can be either extremely sparse or extremely dense. And we're going to find that our procedure does well in all these cases. So what this graph is showing us is each line indicates a different kind of model selection procedure that we could use to choose an interference network. Our model is the one that's solid, and we find that it does a pretty good job across different levels of sparsity. And so our procedure is robust against fluctuations in the interference network. We also try varying the actual model of interference. In this case, we try a case where we just have a single linearly additive model and we have a single interference term, and a case where we have individual heterogeneity. We find that rollouts provide us a mechanism to select between outcome models in both cases. In fact, in the case of individual heterogeneity, this is a case where if we only had one period, we would not even be able to estimate a treatment effect. Yet rollouts allow us to estimate treatment effects and also select an interference model that actually performs quite well relative to the other model selection procedures in terms of estimation error. So the key takeaway here is that rollouts are providing us a mechanism we can use to actually select between outcome models by selecting between interference structures. So now that we have seen how rollout is applied, how can we actually use this to study causal effects? So if we're trying to estimate the treatment effect, we're going to first assume that we've run our model selection procedure and we've picked the true model. The treatment effect we're going to be interested in is known as the total treatment effect, which is the average difference of what happens when everybody is treated versus when nobody is treated. This quantity makes rigorous the idea we previously looked at in that we care about when a treatment is applied to the whole user base. It also has the advantage of being well-defined and interpretable in the case of interference, where the mapping between outcomes and treatments is not necessarily clear. So our goal here is going to be to identify this quantity and also to estimate it. And to do this, we're going to fix a simple linear and means model, where we look at the average of neighbors treated. This is a simple model, and it's used throughout the literature to study interference. And what we're going to find is that rollouts will increase the probability that we observe the sufficient variation we need to estimate this effect. So our first result provides a little bit more of a concrete details for what conditions we need for identification. In the linear and means case that we fixed in the previous slide, an interpretable sufficient condition for identification is that we observe some kind of variation in untreated units. That is, we need to be able to see at some point how an untreated unit reacts to interference, and that will allow us to extrapolate their outcomes to different treatment exposures. This result is essentially saying that if we observe this kind of variation, then we have enough information to compute a total treatment effect. So a natural question to ask is how likely it is that these conditions actually hold. It turns out that in fact, rollouts will increase the probability of identification, i.e. the probability that these conditions are actually holding. The graph we're showing here shows how likely it is that we can identify the total treatment effect in the last example. The probability that our conditions hold is plotted on the y-axis, and the number of rollout periods is plotted on the x-axis. In this model, we're also seeing that sparsity of the underlying network is very important for identifying these interference structures, since these lines are moving up with the density of the underlying graph. However, I think a more interesting takeaway is that the lines are all increasing with rollout periods. In fact, the clear takeaway here is that rollouts help identify parameters that were previously unidentifiable. We're also interested in the statistical properties that rollouts provide us when estimating total treatment effects. To that end, rollouts are helpful in reducing the variance of our treatment effect estimator. For example, in the case of linearly additive interference in a complete interference network, we can make mild conditions in the noise term, such as independence and bounded variance, and show that the efficiency of our estimator increases with the number of rollout periods. Here we have a constant term that will depend on the actual rollout schedule and the max variance of the noise. But the important takeaway is that the variance is decreasing with the number of rollout periods. So what does that actually look like in practice? So we can look at this more practically by simulating more samples and comparing the variance reduction from these additional samples versus the reduction from a rollout. And what we're going to see is that rollouts produce a much more substantial variance reduction. Therefore, another key takeaway is that rollouts also help us efficiently estimate treatment effects. So with that, I'm going to end the talk, but I want to just reiterate some main ideas. The first is that interference is a major problem in experimental designs, and it can affect how we evaluate policies in many fields. Second, rollouts provide us this robust and easily influenceable way to try to ameliorate this problem of interference. And they do that by helping us select between interference models, and they actually provide theoretical gains in identification and estimation of treatment effects. So I just want to thank everyone for listening. And if you're interested in reading the full paper, this can be found on arXiv using this QR code.